global value numbering, which is more powerful than hash-based value numbering. It was one of the first optimizations presented on SSA form, and actually in the paper presenting this algorithm, SSA form was described as well, since it was such a new topic in optimizing compilers. It's said that the IBM uses an unpublished version of the algorithm we will see, which is better than the current version. But of course, I have not seen it. But I would certainly like to. Okay, I would also like to mention that the master thesis student, Morten Kongstad, implemented this algorithm in GCC and saw quite significant improvement. On some codes, this was spec CPU 2000, and some benchmarks improved up to 6.1%, which is very impressive. This was a very well done master's thesis work. Okay, so what's the key idea of global value numbering? We can compare it in some sense with constant propagation, in that constant propagation assumes that only the start vertex will be executed. That's obviously unrealistic, but then it gains more knowledge. Global value numbering does something similarly unrealistic, namely assuming that all instructions with the same operator produce the same result. So in a function, every add instruction is assumed to produce the same result. Okay, given that they are integer add, not floating point add. So the type must be the same. Okay, and the same for all other instructions. And then it assumes that until it's proven false. And then when all instructions have, when the analysis cannot proceed any longer, those which are still thought to produce the same value are checked. And then if one dominates the other, we can remove redundancy. Okay, so what we do is to divide all instructions in blocks or sets. So we partition all the instructions. And the first partition, as I said, all the instructions with the same operator and type are in the same block. Okay, so when are they considered to be equivalent? If we compare two instructions, and if their operands belong to the same block, I mean the first operand of the first instruction and the first operand of the second instruction, if they belong to the same block, then we move on to the next operand. And if they also belong to the same block, then there is no need to think they produce different values. This continues. And we split the blocks when we see that they cannot be equivalent. Phi functions are only equal or equivalent if they are in the same basic block. So let's look at an example. If we have this code, then we can denote the instructions by the name of the variable which is defined. Okay, left A and right A, by that we mean the left or right operand. Okay, so X, Y, and Z, they are unknown, and therefore they are put in blocks of their own. So we have the following blocks: Bx, By, Bz, and then B plus all the add instructions, and B minus both subtract instructions. Okay, so then we can check. For instance, well, we take one block and check all instructions and see if they should still be in the same block. Okay, so let's check E and F, both in the B plus. Okay, so left E, that's A, and it is in B plus. Okay, and then we check left F. Well, that's also A, so it is certainly in the same block. And then we check right E, that's D, and that is in B minus. And then we check right F, which also is in B minus. So we continue to think that E and F produce the same value. Okay, let's then check F and G. Left F is in B plus, but left G is in B minus, so F and G are not equivalent. And what should we do then? We should split the block B plus so that those which agree or are equivalent with one are put in one new block, and all the others are put in another block. They don't have to be equivalent to the other one, but we just put all which are equivalent to one of the instructions. They will still be in the same block, and all others in another block. So we do as follows. We take and create an initial partitioning P0 or pi 0. These are the blocks, and then we say that we continue this until there is no change. Okay, so we take a block, and then we take one instruction called node here from that block and put that in a completely new block. So we take, for instance, the A instruction and put that in a new block. Okay, and then we check all the other instructions in the block in which that instruction was from the beginning. So we check all the others, C, E, F, with A. And if they match, that means if each operand of these two instructions are in the same block, then we put the new instruction in the same block as this one we put first. And if not, we create a new block for the one which is not equivalent to V. And well, we check if we have already created this or not. And if we have not, then there is a change. So we will iterate more. Then we add this other instruction to that block. In the end, we will have found all instructions which are equivalent. That does not mean we can do redundancy elimination, because they have to dominate the others as well. So what we do is to check the instructions in a block in the final partitioning and see if one dominates the other. If that is the case, then B is redundant and can be replaced with the value of A.